Today we are going to be talking about vectors. And what they are, what they mean, why do we care about them? Okay, first thing we got to know is that a vector is anything that has a magnitude. So when I say magnitude, I could be referring to a size, some kind of quantity, right? So a magnitude. It also importantly has a direction. So if we were to think of an example, maybe I would say an example of a vector would be I traveled 10 meters, right? So 10 meters to the right, right? So this 10 meters this is our magnitude. And so to the right, this is our direction. Maybe you can think of a car traveled at 10 kilometers per hour north, and then it turned to the left and started and it traveled 100 kilometers to the west. So those are examples of vectors because they both have a magnitude and a direction. Now we can contrast a vector with this thing called a scalar. So we have vectors and scalars. A scalar, a vector is a magnitude and a direction. A scalar only has a magnitude. And we can kind of think of some examples like, let's take what we talked about earlier. I could say I walked, 10 meters, and that's it. So I walked 10 meters, but if I don't indicate a direction, then I'm talking about a scalar because a vector needs a direction. For example, you could also say mass is an example of a scalar. So I could say I weigh 10 pounds. That'd be ridiculously light, but if that's an example of a scalar, something else could be, speed. So I traveled 10 kilometers per hour, right? So 10 kilometers per hour versus a car travels 10 kilometers per hour to the north. And that is kind of the distinction between vectors and scalars. It's great that we have these definitions, but what do we do with them? Well, the main thing we do with vectors is we're able to add them. So we're able to do this thing called vector addition. And this is really, really useful. This is really useful in the biological sciences, especially because, just off the top of my head, you can kind of think of blood flow as an example of how people can use vectors, and we can use, how fast is our blood traveling, in what direction is it traveling. These are very important things to know to kind of distinguish between different systems in our body and how different aspects of our body uses these systems differently. And maybe off the top of my head, another one could indicate some kind of like ion flow. So how do ions pass a membrane? Do they go through, like, what kind of channel proteins do they go through? And we can use vectors to kind of track stuff like this. So it's really useful to track biological mechanisms within our body. And whenever we're talking about vector addition, we're looking for something called a resultant. So we can call it a resultant vector. So this resultant vector, this is the result. So this is what comes from adding two vectors together. So whenever we add or subtract vectors with each other, we get a resultant vector. Now, what do I mean by adding and subtracting vectors together? Well, there's actually three ways we can add vectors to each other, and with whichever way we use or whichever method we use is dependent on the information that we're given. So let's talk about the first way that we might add vectors together, and we call this the tip to tail method. So this is tip to tail method of vector addition. So let's say we wanted to do vector A. Whenever we want to denote a vector, we're always going to use this little arrow, okay? So you might see something written in bold. Since I'm doing handwriting, I can't write in bold. But a vector always has this little arrow on top of it. So let's say we want to do vector A plus vector B, and then we can say that adds together to form a new vector. We can call it, vector C or whatever. So vector A plus vector B is going to equal vector C. Now, how can we show this? Well, if we're using this tip-to-tail method, we can do something that looks like this. So let's say maybe we draw vector A in this nice pink color. All right, nice. So that is vector A. So let me write that in here. This is vector A. Now maybe we can, now what we're going to have to do is we're going to have to connect vector B. So here's vector B. We're going to have to connect the tail of vector B to the head of vector A. What do I mean by that? Well, this area here, this is the tail. This is the tail region. Over here we have the, this is our head. This is our head region. So we can really connect these two regions together using this tip to tail method. So let's try that out. So let's say this pale yellow color, let's call this vector B. So here is vector B. Vector B. Now the resultant vector, so the resultant vector, we're going to call it vector C, we'll draw it in this red color, is going to be the result, or it's going to be the result of this vector addition. And how we're going to draw it is it's going to go from the tip of vector A, so right over here, and it's going to go all the way to the head of vector B, which is all the way over here. So we can kind of draw these together. Maybe don't do it so terribly as I did it, but to something to this effect, where kind of like the two vectors are going to connect, and this is the tip to tail method, and this red vector is going to be vector C, so it's going to be vector C, which is our resultant. So this is the tip to tail method. So if you're given vector A, which we saw here, and we're given vector B in this form, we can connect them using the tip to tail method to form vector C, which we got right here. Okay, so another thing we can do, I'm going to call this what should I call this? We can call this the components method, maybe components method. That's what I'll call it. I'm sure it has an official name. I'm not sure what it is. But basically, this time, so we're kind of acting in reverse. So this time we had vector A and we had vector B, and we use that information to find vector C. Well, in this case, we're going to start out. So we're going to start out with vector, we'll stick with vector C. So vector C looks something like this. I'm going to change up the shape a little bit. So we had vector C, which looks something like this. Oops. Something like this. We'll call this vector C. Now, every vector has what we call a vertical and a horizontal component. So every vector has a horizontal and vertical component. You can kind of think of it kind of like X and Y. So you can think of an X and Y graph, a Cartesian plane. There's an X axis and a Y axis. Well, it's kind of similar. We can say, let's switch over to this pink color. There's always a, this could be our horizontal. This is the horizontal, or this is the vertical. This is the vertical component of the vector. So we can call this Y. This is the vertical component of the vector, and then there's also a horizontal component of the vector. Right, there's a horizontal component of the vector. And it looks something like this. And we can call this vector X. So these X's, so we have, this X here and this Y here, this is going to be the two components that make up vector C. So we have X and Y to form the vector that we see here. And we can do some really interesting math with this stuff. And at the end of this lesson, I'll really dive in especially into the components method here, because this is probably the one we're going to come across the most. So more on this later. Now, the last version we're going to talk about, the last method we can use, is something we're very familiar with if we've taken high school math. As soon as I write it down, you're going to know what it is. The Pythagorean, so the Pythagorean theorem. Just like that. And this is very self-explanatory. I'm definitely going to go into it more maybe in later videos, but the basic gist of it is if we have vector A, so we're trying to find vector A is going to equal, so the square root of vector A is going to equal, the square root here of vector B plus the square root of vector C. And what does this look like? Well, let's imagine, we can, actually the setup is very similar to this, what we see here. So we have to get a vector, so let's say vector A, right? So this can be vector A, here is vector A, and we have to break it down into its X and Y components. So here is the vertical component that we call Y, we can call this our y. Then here is the x component, our x component that we call our horizontal component. So this is vector x. So maybe I probably should have labeled it vector a and b. So we can call this vector b, and then maybe this is vector c. But my point still stands. So we have a vector a, or the square root of vector a is, or the square of vector a is going to equal the square of vector b plus the square of vector c. And this is very useful when we're given two side lengths. So either we're given the side length of vector a and we're given the magnitude of vector c, and then the question is going to ask us to find the magnitude of the horizontal component of the vector, or some combination of a question like that.